I will record the session. Okay. Actually, we have completed the micro network analysis part. Okay. That is there we have learned several parameters: Z parameter, Y parameter, A, B, C, D, and S parameter. Okay. S parameter is the most important one. So, and also we have few doubts in when we are finding those things. Okay, we have doubts. Okay, what happened to that current? I think we have problems. Okay, so anyway, that problems are sorted out, but we will discuss them on our next interaction session next Wednesday. Okay, so now let's assume that we have completed the parameter, S parameter, A, B, C, D, and Z parameter. Okay, so I think we have done enough example for Z parameter and A, B, C, D parameter. Okay, but I think if we can do another one or two example for S parameter, it will be better. Okay, so we will try to do it also in our next interaction session. Okay, so today we hope to go to a new session. Okay, that is microwave component design. Okay, so that is a new topic. I think it will be okay with you. Okay, give me a moment. Okay. Okay, now we need to move to new session. Okay. That is, I think you can see my writing, no? So we have basically, we have done network analyzing part. Okay, network analyzing part. Microwave network analyzing part. Okay, so there we have learned basically 4 parameters. Okay, this parameter. Okay, so we have done enough example on this one, and also we have done enough example on this one. Okay, so we I think for a Y parameter we didn't do any example. That is okay. We just get the idea only. Okay. And S parameter, I think it is better if we can do 1 or 2 example in our interaction session. Okay, in our interaction session. Okay, so I think you can try actually this. Okay, so in our reference book there may be examples. Okay, so you can try to do 1 or 2 example. Okay, if you have any problem, we can discuss them. Okay. So try to do it. Okay. So we have completed almost this analyzing part. Okay. Now we are going to do a new session. We are going to come to a new session, that is microwave component design. Okay. Component design. Okay. So under this topic, we hope to learn basically, at least we will try to learn, we should learn how to design a low pass filter. Okay. Then coupler, amplifier, oscillator. Okay, oscillator. Okay. So I hope to do this 4 component designing criteria. Okay. So definitely we can do this one, and we should do this one. Okay. And we will try to do this one also. Okay. And if we have time, we also try to do oscillator design. Okay. So for your exam, you will get the question from low pass filter and coupler. Okay, only these 2. Okay, and we will do assignment in this one, amplifier. Okay, so oscillator is just for our knowledge. Okay, there is no any evaluation method there. Okay, so we will try to do these 3-component design criteria, and if we have time, we will come to oscillator part also. Okay, so today we are going to discuss about LPF or microwave low pass filter. Okay, microwave low pass filter. Okay, I think you know what is a filter, no? I think already know what is a filter. Can anyone tell what is a filter? Can anyone just one sentence? Okay, so actually it is a device. Okay, it is a device that give us a desired frequency band. No, desired frequency band on the input of a frequency, some frequency bands. Okay, so if we give a input, okay, if we give a input, so there can be a frequency band. Okay, and this will give us a desired frequency band. Okay, so desired frequency band we will get. Okay, for example, let's say that this is a radio. Okay, radio. Okay, and our channel is working on 88.1 megahertz. Let's say that. Okay, okay. So you want to tune this, you want to catch this channel, okay, for your radio set. Okay, so what you can do is you can put the filter here, so you know that so this is a radio. Okay, so wireless transmission is there, so antenna is used to catch the signals. Okay, so you know that for this antenna some frequency band can be induced, okay, in this antenna. Okay, several. Okay, not only this one. Okay, so what we have to do is we can use a filter here. Okay, you can use a filter here. So once you get some frequencies, unnecessary frequencies, and this frequency, you can cut off this unnecessary frequency and get the desired frequency band on it. Okay, so that is a basically filter, frequency filter. Okay, okay. So it is actually a frequency domain device. Okay, so this is working in a frequency domain. Okay, the filter is working on the frequency domain. Okay, so that is it. Okay, and I think okay, so another thing is in your signal and system, maybe you have learned that if we have a system, okay, if we have a system, and if it is LTI system, okay, so these informations are not needed for our course. Okay, but this is the beginning. Okay, actually. Okay, so that is why I want to remind you this. Okay, so if we consider LTI system, I think you have learned these systems in signal and system. LTI system means linear time invariant system. Okay, invariant system. Okay, and for LTI system, okay, so almost every system we consider as LTI system. Otherwise, the derivations are very hard. Okay, so we need to get the input and output relationship. Okay, so if it is linear and time invariant, we can easily get the input and output relationship of a system. Okay, so if it is not linear or time invariant, maybe it is somewhat complex. Okay, so normally we are considering LTI system. Okay, so almost all the system we are working with are considered as LTI system. For example, this filters, couplers, amplifier, oscillators, those are considered as LTI system. Okay, so if you consider LTI system, okay, so if you give a signal, Okay, if you give an input, let's say that it is a time domain signal, and you have output. Okay, and the process is there. Okay, filtering, application, any process is there. Okay, that process is described by what is called HT. Can anyone remember what is this HT called? කාට හරි මතකද මේ HT කියන්නේ මොකක්ද කියලා? What is this HT? Yes, very good. That is impulse response. This is the impulse response. Okay. Impulse response is if you give an impulse to a system, delta T impulse, okay? So system output is referred as impulse response, okay? So if you are given, if you give a impulse, delta T signal, okay? You know what is the impulse? Impulse is like this, okay? So this is a complete mathematical signal, okay? This is completely mathematical signal, okay? So you know that the area should be this duration should be 0 and area should be 1, okay? So this is going to up to infinity. So normally you put 1 here, okay? So that is referring the area, okay? So that is a very complete mathematical function, okay? Complex mathematical function, okay? So it is not a practical thing, okay? It is a mathematical signal, okay? What is called that? It is a hypothetical signal, okay? It is not practically available. We can't practically generate the impulse, okay? But practically we can generate this kind of pulse, electrical pulse, voltage pulse, okay? For the impulse, this duration should be 0 and the area should be 1, okay? So this should be very narrowed, then it is, should go to up to infinity like this, okay? It should be very narrowed. This width should be 0, okay? So it is just like this, okay? We represent this using arrow, okay? So the impulse response is nothing but once we give an impulse to a system, okay? Once you give an impulse to a system, the output is referred as impulse response, okay? And I think you have known the input and output relationship of LTI system. That is YT, the output is equal to XT convolved HT. This is convolution, okay? This is not the simple multiplication, that is a convolution, okay? So there is an integration actually, okay? So integration is like this. I think you can remember maybe XT minus tau, H tau like this, D tau, okay? So actually this is not a normal integral also, okay? Because there are two variables, this tau and t, okay? So you have to consider all this tau and t, what is called, all this tau and t range, okay? So it is somewhat hard to do this convolution, okay? So anyway, this is the input and output relationship, okay? So there is a convolution, okay? So if you want to find this HT, impulse response, you have to do the inverse convolution, okay? So I don't know inverse convolution is possible or not, okay? I don't have idea, okay? I haven't learned about the inverse of a convolution, okay? Maybe that kind of thing is there. You can check it with mathematics teacher, okay? So anyway, it will be very hard. You know that this convolution is also very hard, okay? So if you are doing the inverse process, it will be more difficult, okay? If it is possible, okay? I'm not sure it is possible actually, okay? So so actually you can't find this HT using this input and output, okay? Because there is a convolution, okay? So we have to do another things, okay? So what we are doing here, this is in time domain, okay? So we are normally converted to another domain, okay? So you can convert this into frequency domain using Fourier transform, okay? I think you have learned. Don't worry, okay? We are not going to learn these things, okay? You no need to know the Fourier transform, okay? So don't worry, I'm just coming from the beginning, okay? So Fourier transform, you can convert this to a frequency domain, okay? And in another popular domain is S domain, what is called S domain, okay? So this is actually complex domain. This is we called complex domain, okay? So you can use Laplace transform. Laplace transform to convert this time domain into a complex domain, okay? So this is frequency domain and this is complex domain. Frequency domain, you know, sometimes referred as omega. This is angular frequency measured in radian per second. This F is the normal frequency measured in hertz, okay? So if you convert this from time domain to frequency domain, what happen is that, okay, this multiplication become, this convolution become a multiplication, simple multiplication, okay? So that is we called actually convolution property. Convolution property of Fourier transform or Laplace transform. The property is same for both transformation. Fourier transform or Laplace transform, okay? So once you convert this to this into frequency domain, this convolution or frequency domain or complex domain, this convolution will become a multiplication, okay? So you can write this as, okay, so if you write it in frequency domain, you can write like this: y omega is equal to x omega into h omega, okay? Or in complex domain, you can write this: ys is equal to xs and hs, okay? So if you are learning control system, okay, normally we are using this S domain, okay? S domain stuff, okay? And for this one, we are using this frequency domain because you can understand that the filters or amplifiers, oscillators, those are directly related with frequency, okay? So we can use this frequency domain analysis, okay, rather than using S domain, okay? So both are same, okay? Actually, instead of this S, what you have to do is you have to apply j omega. So you can convert this from S to frequency or frequency of S, okay? So it is very simple. So now we are mostly focusing on this frequency domain analysis, okay? So once when we are converting, if we are talking about in frequency domain or S domain, this has another name actually. Normally it is called impulse response when it is in time domain, okay? This is time domain, we called it impulse response, okay? And in frequency domain, what is we called? Frequency domain S domain, what is this called? That is the frequency domain or complex domain quantity on the impulse response, okay? That is we call transfer function, okay? This is we call transfer function, okay? Actually the frequency domain or complex domain representation of impulse response, that is called as transfer function, okay? So if it is in frequency domain, we called it frequency transfer function, okay? Frequency transfer function. And if it is S domain, we called it complex transfer function, okay? Transfer function, okay? Okay, so normally we are focusing on frequency transfer function, okay? So if you consider frequency transfer function, okay, so now we have a system. Let's take the filter, okay? let's take a filter. Okay. And if you are given frequency domain signal x omega, okay, so this is a frequency band actually. Okay, so you have output y omega, and there is a transfer function, frequency transfer function for this filter, that is h omega. Okay. Okay, so now you can write h omega is equal to y omega divided by x omega, because here we have a simple multiplication. Okay, this is not a convolution, it is a multiplication. Okay, so now you can write this transfer function as y omega into y omega by x omega. Okay, so you have to know this one. Okay, so this is the transfer function. Okay, okay, now based on this transfer function, okay, based on this transfer function, okay, we can divide a filter into three types. Filter into three types based on this transfer function. Okay, based on this transfer function. There are many filter types. Okay, with the implementation. Okay, and if we are using analog digital, based on analog digital component, you can classify a filter into as analog filters, digital filters, and based on the impulse response. Okay, based on this impulse response HT, you can define the filter into another two. Can anyone tell, based on this impulse response, how we can divide the filter? Maybe you haven't learned. Maybe in DSP, I think you are learning this. If you have done the DSP, I think you know. We called it finite impulse response filter, FIR filter, and infinite impulse response filter, IIR filter. So FIR, IIR filters are there. Okay, and if you are in digital system and digital and analog system, analog electronics, you are learning about filters. Okay, so that is based on the component used. Okay, so we basically divide into digital and analog filter like this. Okay, and based on the transfer function, that is, I think, the most popular classification. Okay, based on this transfer function also we can filter into three types. What is that? I think that is the most popular classification. Everyone knows this. What is this? I think the first year student also know this. Not only. Okay. There are three types. What are they? So this is one, your answer is correct. This is one type. Low pass filter is one type. What are the other types? Yes, very good. Okay. So there are three types actually. Basically, low pass filter, high pass filter, and band pass filter. Actually, four types are there. It is called band stop filter. Okay. So these are the four types. Okay, four types are there: band pass filter and band stop filters. Okay. So for example, when we are talking this, okay, so this scenario is we are talking about a band pass filter. No, we get a desired band 8.8, and that is a band pass filter. You have to use a band pass filter there. Okay. So actually in your radio set, you have a tunable band pass filter. Okay. So band pass filter, tunable analog band pass filter is there. Okay. So change in the capacitor value, you can tune it to different frequency. Okay. Okay. Now we are learning about low pass filter. Okay. So basically there are four types, but now we are focusing on this low pass filter. Okay. And once you learn this low pass filter design criteria, you can easily learn this high pass filter, band pass filter, and band stop filter. Okay, actually there is a mapping. Okay, so you have to map this to LPF uh, response, and BPF also should be uh, mapped to the LPF response. This BSP also should be mapped to the LPF pre LPF response. Okay, this if you want to design a high pass filter, okay, so first you have to map this high pass filter response to a low pass filter response. Then based on that, you can calculate the component value. Okay, so that is the normal procedure. If you want to design a band pass filter, you can convert this to low pass filter. Okay, convert it to low pass filter, map into low pass filter response, then you can calculate. Okay, so you can do the designing process so as band stop filter. Okay, note that one. Okay, so that is very important point. Okay, so we should first know how to design a low pass filter. Okay, if you are okay with this LPF design, then you can easily go for other design, high pass filter, band pass filter, and band stop filter. There is a specific mapping procedure. Okay, so if you know the mapping procedure, you can design this high pass filter, band pass filter, and band stop filter easily. Okay, so that is what you have to understand. Okay, so if you want to, if we talk about the response of this low pass filter, the low pass filter responses look like this. I think you know this. Okay, it is like this. Okay, actually this is the ideal. This is the frequency. Let's say that this is omega. Okay, the frequency in radian per second. Okay, so this is h omega. Okay, so this is the response. Okay, response is like this, and we call this omega c, cutoff frequency. This is called as cutoff frequency. Okay, so this is the ideal response. Okay, and for high pass filter, it is somewhat like this. Okay, like this. Okay, so this is the high pass filter, and this is h omega. This is omega. Okay, so you can see that filter is pass in this, not pass in this section, and it pass in this one. Okay, so this is called omega p pass band. Okay, so this is we called as a pass band. Okay, and for a band pass filter, okay, it is like this. Okay, and band stop filter, it is like this. Okay, it is like this. Okay, so this is lower pass band. This is called pass band H frequency, lower pass band H frequency. Then this is higher pass band H frequency. Okay, like this. Okay, so these are the ideal response for filters. Okay, I think you already know this. Okay, so I'm not going to explain this anymore. Okay, you already know this is okay. So actually, these are just ideal for filters, ideal filters, but practically this response is not like this. Okay, we will see this. Okay, it is not like this. Okay, and this h omega, you know that h omega is already, you know that y omega divided by x omega. Okay, actually, what is this? Can anyone tell what is this? What is this? So there is a system, there is the input, and there is output. Okay, so if you divided y omega input, output divided by input, what is this? What is this we called? මේකට මොකද්ද කියන්නේ මකයද? This is actually transfer function. Okay, this is the transfer function, but another parameter also here. What is that? In other words, this is the gain, no? Is this okay? This is the gain, no? Okay. So if you divided input from the output, that is the gain. Okay. We called it gain. Okay. Remember that one. Okay. And if you divide x omega input y omega output, what is this? What is this? Yes. Very good. That is loss. Okay. That is loss, or sometimes referred as attenuation. Okay. Sometimes referred as attenuation. Okay. This is correct, no? Output divided by x omega, that is called that gain, and input divided by output, it is called as loss. No, I think that is correct. Let's check anyway, because I can't remember this term actually. Okay. So let's say that gain gain and loss. Let's say that amplifier or something. Otherwise, we will take. Yeah, gain is output divided by input, no? Okay, output power divided by input power, that is the gain. Okay, and definitely other is the loss. Okay, that means input divided by output, that is loss. Okay, so that is clear. Okay, so we are correct. Okay. Okay, so anyway, that is correct. Okay, I hope that is correct. Okay, the gain is output divided by input. Okay. Okay, uh, so I think we are correct. Okay, the gain is output divided by input, that is we called as gain, and input divided by output, that is the loss. Okay. uh, okay, now you please remember it. Okay, so if you have any doubt, please refer our books or internet, then remember this one. Okay, this one also very important. Okay, so sometime you may give a gain, no, sometime you may give a loss curve. Okay, so this is the gain curve, okay, of a filter. If you are given a loss curve, that also can be given. Okay, so you can calculate the loss gain using the loss. Okay, using this loss value, you can calculate the gain. Okay. Okay, so another question, I will ask a question. Okay, so if you have amplifier, gain should be plus or minus. So let's say that, sorry. Okay, let's say that you are uh, normally you are measuring this gain using dB. Okay, using dB. This is a ratio, input divided by output. Okay. Okay, so for a ratio, we like to use dB. You know what is dB? Okay, so we are putting 10 log 10 to the system y omega divided by x omega. Okay. Yeah, yeah, you are correct. Okay, so that is uh, that is the gain in dB. Okay, so this is the gain in dB. Okay, so you have already know this. That is why I'm not going to do any calculation or something. I'm just give you a quick recap. Okay, okay. So the gain can be measured in dB. Okay, so if you are measured in dB, so you get the ratio, and if you put 10 like log 10 into log base 10, you can calculate the dB value. Okay, now my question is, if you use amplifier, this gain is plus dB value or minus dB value? Yeah, I got the answer. Yeah, I got, yeah, very good. It should be positive, no? It should be positive, because uh, for amplifier, the output may be high. The output power should be high. So the output power is high and input power is low. Okay. So you will get 1 point or something value. Okay. So the value is greater than 1, definitely. Okay. So if you get 10 to the log 10, you will have plus value. Okay. And what about the loss of amplifier? What about the loss of amplifier? Is it plus or minus? Let's say that someone say that the gain of the amplifier is 10 dB. Then what is the loss of the amplifier? What is the loss of the amplifier? The loss of the amplifier is positive or negative? Okay, so if you consider amplifier, the input is there and what output is there. Okay, so loss is equal to input divided by output. Okay, input divided by output. Okay, so for amplifier, so the amplification is there. Okay, so y omega is definitely high, x omega is low, input is low and output is high. Okay, so what happened? For a loss, you will get a value less than a 0. It will be a decimal value, 0 point or something. Okay, so if you put 10 to the power log 10 to a decimal value, the value less than 0, you will get minus value. Okay, for amplifier, loss is a minus value. Okay, so someone say the gain is 10 dB, the loss will be minus 10 dB. Very easily, you have to change the sign. Okay, so 10 dB means nothing but 10 to the power log 10 y omega x omega. Okay, okay, so this is the gain. Okay, so if you want to find the loss, okay, that is 10 to the power log y omega x omega, sorry, x omega y omega. Okay, y omega. Okay, so here you have a minus value, no? So you know that log 10 to the power 100, it is equal to 2. 10 to the power 2 is equal to 100. Okay, then log 10 to the power 1 divided by 100, what is the value? It will be minus 2. No, 10 to the power minus 2 is equal to 0 0.01. Okay, so here, if we, so here uh, it is the what is called reciprocal, na? We called it reciprocal or something, no? Anippatta. See, na? එකයට C. If you have 100, it should be 1 divided by 100. Okay, so here it is y omega, x omega. Some value is there. Let's say that x. Okay, so if you get 10 to the 10 into log 10 to the base x, that is 10. And if you get 10 to the log 10, 1 by x, you will get minus 10. Okay, so the sign is also changed, only change. Okay, so you have to understand this. Okay, so what you should know is that based on the transfer function, we can divide a filter into four types. Okay, low pass filter, high pass filter, band pass filter, band stop filter. Okay, so for high pass filter, so if you consider low pass filter, so the band, this should be, okay, so here h omega is nothing but y omega divided by x omega, no? Okay, y omega divided by x omega. So you have a value there. There should be a gain, no? Y omega and x omega, there should be a gain, plus gain. There should be a plus gain value. Okay, and after cutoff time, there cannot be any signal, no? So the output should be 0. The output should be 0. Then if the input is, the output should be 0. So you will have 0 values. Okay. Okay. So your ideal filter response should be like this. Okay. For a pass band, there should be a gain. Y omega should have a value. And sorry, not sorry. For a filter, if you consider filter, this gain is plus or minus. Gain is y omega divided by x omega. Okay, so this is a passive filter. Let's say that it is a passive filter. There is no any amplification. Okay, so if you have a filter and you are given an input and you have output, okay, then what is this gain value? Is it plus or minus? Please tell me. Please think and tell me. Is it plus or minus? This is a passive device. Okay, there is no any multiplication, but there can be loss. Definitely, no? Yeah, it should be minus. Okay. Yeah, very good. It should be minus because you know that this filter is a passive. Okay, this filter is a passive device. There is no any multiplication, but loss can be there. Connection loss, and also these passive filters are normally, you know that it is LC LC network. Okay, so resistors are also there due to a line. Okay, so the losses can be there. Okay, so definitely the value of the input should, the power value of the output is definitely less than the power of the input. If you are given high power as an input, but the output will have a low power. Okay, so the filter response is not a plus value, it will be a minus value. Okay, the gain, filter gain will be a minus value. But if you can consider amplifier, that gain should be a plus value, greater than 0. Okay, so this should be a minus value, less than 0. Okay, it should be a minus value. Okay, don't forget it. Okay, so it is a minus value. For a filter, the gain should be a minus value. Okay, so anyway, after pass band, there should not be a output power. Output power should be 0. Then after that, you have 0 value. Okay, so same way you can understand this response, and this response. Okay, so try to understand it by yourself. Okay, okay, now we will move to our design criteria. Okay, designing procedure. Okay, so you have the basic idea, you should have this basic idea, then we can easily continue. Okay, so I will share the screen again. Okay, so if you consider our, what is this? So if you consider our microwave David Posabu, okay. You can see the chapter 8 is the microwave filter, okay. So you can go through this chapter, okay. You can read if you have any problem, okay. So complete description is there, okay. Complete description is there, okay. Uh, uh, so there are many types of many methods of filter design, okay. So, so there are many methods, okay. So this is also another method. Okay, actually this is you can see that, okay. This is a low pass filter response, okay. This is a low pass filter response, okay. So what we have right there, what we have seen there is like this, you know, up to here it is 0, up to here it is have a value 1, then it is 0. But here vice versa is there. What happened here? Actually, previously we consider the gain, but this is a loss, okay. This is a loss. Here for a filter function, he consider the loss, okay. So that is why the response is vice versa, okay. Is it clear? Okay, I think here, okay. So normally our filter response is like this, okay. So if you have a elliptic, that is called, okay. So you will have this kind of one, definitely. Okay. There are some ripple here like this, and you have a response like this, and here also ripple, okay. So this is the elliptic filter response, okay. So, but you can see that this is vice versa, no? තේරෙනවනේ කියන එක. හරි? ඒක එක එක විදිහට තියෙනවා, but if you know the basic, you can understand anything, okay? So, here it is written like this. What happened? Here we consider the gain, but here we consider the loss, okay? So, loss and gain can be given. The both response can be given. You should know how to use them, okay? So normally for the filter design, we are using the gain response. Okay, when that method we are going to learn here. Okay, but sometime when we are reading the book, you can get confused. That is why I am explain that one also. Okay, don't get confused. Okay, if you have any question or any problem, you can ask me. Okay. Yeah. So you can see that here the low pass filter design is there. Okay. Low pass filter is designed there. I think our method is this one. We are going to use this method actually. Yeah, we are using this method, okay. Insertion loss method, okay. We are going to use this method for our design, okay. So this is the design process, okay. First, use the filter specification, okay. For the filter specification, we need to get this filter specification, and we have to consider the response also. Then we can uh, do the prototype design, then come to the scaling and conversion, then the implementation. Okay, we will check this. We will see this step by step. Okay. So that is the normal procedure. Okay. Okay. So the insertion loss means now we are going to actually here it is consider the loss curve. Okay, loss response. Here we use the loss curves, but we can also use the gain response also. Okay, instead of this insertion loss. Insertion loss is referred as the so that is when you are input something, there is a loss, and that is called as insertion loss. Okay, so maybe you have learned these terms before. I'm not sure. Okay, anyway, don't confuse with these terms. Okay, once you have designed one filter, you will be okay with the designing process. Okay, so okay, so we will go through this step and try to design one. Okay, uh, and here the filter transformation. Okay, so I told you that if you want to design high pass, band pass, or band filter, band stop filters, we have to do a mapping. Okay, that is called as transformation. Okay, so we have to map that response to a low pass filter response, then we can do the design. Okay, so this is also this considering the losses. Okay, this are also considering the loss curve, not the gain curve. Okay, here we are considering about gain curve. I think you are familiar with this. Okay, correct. Okay, you are familiar with this gain curves, gain response, but sometimes loss also can be considered. Okay, here for the transformation also loss is considered. Is that okay with you? Okay, so we are doing example, then you can understand. Okay, so if you can't, if you didn't understand complete these things, that will be okay. Okay, later you can understand. Okay, then you can do the design. Okay, so so that is how our procedure, the filter design steps. That is those are our filter design steps. Okay, so anyway, the basic is the low pass filter. We have to learn that one before going for other filters. Okay, so let's move to the low pass filter design. Okay, so actually for that one, I am not going to refer this reference book. Okay, reference book. Okay, but actually I learned these things from Professor Anura Gunawardhan. Okay, he's a professor at Peradeniya University. Okay, so he is my teacher. Okay, and actually I learned this through his note. Okay, so he has given a very good note actually. Okay, so I hope to use that one for our design process also. Actually, I didn't get any permission to use it from him. Okay, so I don't think it will be a problem. Okay. Mm, okay, so this is the low pass filter design. Okay, actually, uh, I these three videos completely describe um, very potentially describe how to design a filter. Okay, so I like if you can go through these lectures. Okay, um, rather than going through my lecture actually. Okay, so if I can get the permission to share these videos with with you, I will definitely give this to you, okay? Before giving, I have to get his consent, okay? Otherwise, it is not proper, okay? So actually, I like if you use these 3 lectures rather than going on my lectures, because this is very what is called very, it has a good potential and it is very sophisticated, okay? So anyway, so this is the note. Can you see my screen? I'm sorry, you can't see the screen, no? Okay. So these are the, now you can see my screen, no? Yeah. So this is the note, okay? I am going to use, okay? So that is Professor Anura Gunnaratana notes, okay? And these are the lectures. 3 lectures are there for filter design, low pass filter design, okay? So I like if you can go through this lecture, okay? Anyway, I will try to give this to you, okay? Okay. So anyway, this is the note I'm going to use, okay? Uh, so for this section, I will use this note, okay? Because the information should be with you, okay? And I also share this document with you. Then you can, there is a example also, okay? Uh, so anyway, we will stop here, okay? And we can in next week or maybe tomorrow. No, tomorrow we have another session, no? The online session, okay? So we will begin our low pass filter design at that session, okay? Tomorrow, okay? So, so I think please try to recap the previous things, then it will be easy to go through this lecture, okay? So we will do this, we will start this tomorrow, okay? So this is, so actually when we are talking about filter, okay? Based on the response again, okay? This response type, okay? Uh, Again, the filter can be divided into 3 types: Butterworth, Chebyshev's, and elliptics, okay? So in this course, we are mainly focusing on Butterworth and Chebyshev's filters, okay? Not elliptic, okay? So Butterworth means the response is somewhat flat, okay? So you can see that this is the gain curve, okay? So this is the gain curve, okay? For this one, the gain curve is used. So you can see that it is like this, okay? Here, here. That is for ideal filter, ideal low pass filter. But practical filter, it is somewhat like this, okay? So here it is not a sharp edge, okay? But this kind of decreasing edge is there, okay? So this is the response for a Butterworth filter, okay? Butterworth filter. And you can see that in this pass band and stop band, this is we called as pass band, okay? Okay, and this is we call that stop band, okay? And there is some frequencies are defined here. Here this frequency we call that is stop band H frequency, and this is called as pass band H frequency. For your design, this should be given, okay? These are should be given, or you have to decide them according to the application. Okay? According to the application, you have to decide them more. You are given, okay, these things, okay? Actually, you are given based on the application, okay? Based on our requirement. This should be, we can define this, okay? According to our requirement, okay? And the Chebyshev filter, for a Chebyshev filter, you can see that the ripples are there. Okay, so this is Chebyshev. Okay, so you can see that in passband there is a ripple. Okay, this is called ripple. It is not constant. It is the previous one we called flat response, but this is not a flat. Okay, there is a ripple. Okay, so this is a Chebyshev type, okay, and uh, for a elliptic in passband and stop band, both stop and passband, there are triples, okay. So, so that is it. We are going to learn those two types, okay. So it is easy. Don't get serious, okay. So if you can see the equation, those equations are very straightforward equation. So you have to apply the value where get the calculate the component, okay. You also no need to keep remember any of this equation, okay, for exam, okay. So you are given this equation, okay. So there are set of equation you have to use, okay. So this equation will be definitely give you, but only thing you have to learn how to use them, okay. So that is very important, okay. Okay, so then tomorrow we will see how to design a low pass filter using that method, insertion loss method, okay. So I hope you got the basic idea. Then I think easily we can start, okay. Okay, so thank you for the participation. Tomorrow we will go for a low pass filter design, okay. Okay, thank you for the participation. I'm sorry for the late, okay. Okay, thank you. Okay, thank you. Okay, if you don't have any uh, issue, can we wind up? Okay, so we will wind up. Okay, so thank you for the participation. Thank you.